Okay. So good morning, good afternoon, good evening, everyone. I'm Koji Yamashita from UC Riverside, who serves as the moderator of this webinar. Welcome to the IEEE PES foothills section. Our foothills section encompasses a vast geographical area stretching from West Covina to the eastern end of California and from Temecula to Baker. Professor Kyung-Fu, it is great to have you today. Welcome to the IEEE PES foothills section. Before starting your presentation, let me introduce your bio. Professor Kyung-Fu, who is a senior member of IEEE, is a seasoned professional with expertise in academia, research, and industry. He holds PES and MS degrees in electrical engineering from Yonsei University, Seoul, South Korea, and earned his PhD in electrical and computer engineering from the University of Texas at Austin, USA in 2007. Professor Fu's career spans roles such as R&D engineer at Samsung Electronics, South Korea, and grid operations engineer at the ERCOT, USA. He contributed to grid operations and planning research at the US EPRI. Since March 2010, Professor Fu has been a professor at Yonsei University, leading the Smart Grid Research Group. His research focuses on dynamic performance modeling, analysis, and control of power grids, emphasizing renewable energy resources and data-driven approaches. And actively involved in IEEE, Professor Fu serves as the secretary of the IEEE Seoul section, and he received an IEEE PES Technical Committee Working Group Recognition Award in 2022. He also contributes as the lecturer in the IEEE PES General Meeting tutorial session on HVDC planning. That is wonderful. So I'm going to stop sharing. Okay, so Professor Fu, fire away.
Thank you, Koji, for kindly introducing me. So let me, can you see my screen?
Yes, it's clear.
Okay, so good afternoon, everyone. I'm so excited and pleased to join this webinar of IEEE PES foothills section. I'd like to thank you all for participating in this webinar, and especially Dr. Koji Yamashita for kindly inviting me to this event. So my name is Kyung-Hur. I'm a professor at Yonsei University, Seoul, Korea. So I belong to Seoul section, region 10, and I serve as a secretary. Today I'm going to talk about quite a universal topic, modeling and analysis of electric power systems. These are very crucial in almost everything of electric power systems engineering. These become more crucial because of increasing renewables, which are variable, distributed, power electronics interface, often represented as an inverter or converter interface to the power grid. So I put IBR challenges in the title to generally introduce some collaborative efforts with Korean utilities. Well, we have KEPCO, Korea Electric Power Corporation, a single transmission owner, and Korea Power Exchange, KPX, which is an ISO, to deal with these challenges. So I may say those efforts are actually universal. Indeed, we studied NERC disturbance reports, and I understand that IEEE 6, Region 6 is the home of all of the IBR challenges. Also the frontiers, so basically to develop the mitigation and corrective measures. But I hope you could find what is happening in Korea interesting and informative as well. So before jumping into some technical issues, I'd like to introduce Yonsei University, located in Seoul, Korea. It's the oldest. It was founded in 1885 by the U.S. visionaries, actually, who recognized the value of education. It's one of the highly regarded university in Korea. It was actually among by the regarded University Reputation Institute. It was regarded as the number one in actually among the Asian private universities recently. So you can see some beautiful photos. So I'm in Sinchon, yeah, Seoul campus, along with some medical uh, school and hospitals. We have other campuses, especially for international. Okay.
Hey, AM Warland, can you please mute yourself? I think you forgot to mute yourself. That'll be really nice. Thank you.
Okay, thank you. So I also included some photos of the Yonsei. So, okay, I'd like to take advantage of this great opportunity to introduce Yonsei University to you for the benefit of those who are not really familiar with Korea. Right, okay, so also, it's a big university, very large university. So we have more than 40,000 students, and about 14% is actually from the foreign students. Actually, it's very close to the penetration, the renewable penetration level in Korea. So about more than 5,000 students from. Also, I think 1,000 students from the US, I guess. Okay, so that's much for the Yonsei University. Okay, so I'm going to talk about now some technical issues that I mentioned earlier. So again, it's a global challenges. Okay, so Korea is also in big transition to carbon neutrality. Okay, we want to be carbon neutral by 2050. So we'll have lots of renewables, and they are making some issues. And I selected some issues. So that is basically coming from the changing dynamics of the grid. So we often say the grid becomes weaker. It means that their voltage and frequencies are quite sensitive to disturbances. Okay, it's a big control system, and the voltage and frequency are the big, very good indicator of the health. They are very vulnerable to disturbances. And especially, I'm going to talk about one of the issues that growing credible contingency. So it is a so-called frequency, a voltage-induced frequency event. So I will elaborate on that later. So that we are talking about how we can handle this issue. So by having, establishing optimal reserve requirement. So we're finding the reserve requirements. Also, up until now, renewables are connected to the grid without really having some requirements. So, but we are imposing strong requirements to the grid, as you do, as many countries do, right? So that I mentioned that is a kind of universal topic. And many of the topics will be actually based on my recent paper published last July in the proceedings of the IEEE. I had a great chance to publish this paper. So you may want to see that paper as well. And also one of the big trend is in the planning and operation studies is up until now, we relied on so-called PSSE, PSLF studies, phased domain studies, right? But now the importance of EMT studies are, emphasized. And so I will talk about this issue as well. Okay, we want to improve our practices, okay, to handle the changing dynamics of the grid due to renewables, especially focusing on the Jeju. It's not scaled. Okay, so the Jeju Island is not that big, okay, with reference to the mainland, but it's just the Honam area, so the most area mainland of South Korea. Okay, and I will conclude my presentation. Okay, so Korea now wants to talk about our issues in the conferences. Up until now, renewables, that penetration level is not really high. We didn't experience any serious problems you could easily find from IEEE region 6. But now renewables have been growing. So it's a changes and large deviations in the typical 24-hour load profiles in October, okay, from 2017. So let me change my pen to, okay, laser point. So 2017, rainy day, October. So that is a off-peak season. Okay? Our problems are highlighted in the off-peak season. Actually, so rainy day, sunny day, you see the difference, okay? But now the difference becoming, okay, greater, okay? And it causes many issues. So also they are in inverter-based resources, so they can impose the new dynamics, okay? Power system engineers have not experienced up until now, okay? Also, we don't have adequate tools to see those dynamics in advance. That's one of the reasons that we are, actively talking about these IBR challenges, right? Also mitigation measures. So it's actually a phrase from Ryan Flint from NERC. Okay? Omnipresent peer that a single phase event leading to blackout. It actually happened in Korea. Okay? So also increasing contingency size. Okay? So we have a credible contingency list that is often, generation trip, okay, one of the generators, one generation trip or two generation trip or transmission line trip. But now we have uncertainty in the contingency as well, okay? We are quite, so we often experience kind of enlarged contingency, okay? That is due to voltage. The DVRs, they are very sensitive to voltage. They are simply tripped. And because we lose power from the inverters, inverter-based resources, so we can also experience frequency events. And it can affect the whole grid. And we are very concerned about this. Okay? So our existing contingency plans, okay, for those contingencies, okay, may not work. Okay, so our contingency plans are not credible any longer. There's an issue. So we have to improve our planning and operation strategies as well accordingly. So typical. So with the KPS, this is not a big actually topic of my presentation today, but we are actually improving the grid ancillary services, okay, to handle that variability issue. Okay. So as I briefly had a chance to talk with the Kosi earlier this morning here in Korea, and actually we are improving that one. And so when it comes to so we say variable renewable resources, but we have improved the forecasting technique so that somehow we can predict the variability, but somehow still, okay, it cannot be perfect, right? Forecasting accuracy cannot be perfect. We still see some uncertainty, and we have to handle that uncertainty, and that comes from the reserves, right? Okay, so we are in a stage to improve our operating reserves. Okay, so especially by including the faster frequency response, that includes the grid forming services from the ESS as well. Okay, so and actually it is basically the forecasting error, but we didn't do I mean, it's just that this graph just shows the trend only, okay? But we should see some deviation from the actual output from the forecasting value, right? So it is to emphasize that one. But somehow by improving the forecasting tool, we can somehow minimize the uncertainty. Then somehow we can optimize the reserves as well, you may say. Okay, so also impact of DR modeling. We can, in the planning stage or so operational planning stage, we have to be, aware of that impact, right, of the contingency. But the issue is that up until now, our models do not represent the dynamics of the load, okay, also including DRs, okay, so-called the BTMs. So in many practices, planning practice even, load modeling, negative load has been used for representing the distributed energy resources, okay, in PVs basically, okay, also behind the meter being part somehow. And if we just stick to use the existing load model without any dynamics, okay, it is sensitive to voltage shift. Okay, load shedding mechanism is included in the part, but this does not capture the DERs. Also, even up until now, those PVs are not regulated in the interconnection stage, but we are imposing new standards, say ride-through capability, low voltage ride-through capability. We have improved those low voltage ride-through capability and also strengthened the standard. Somehow we have improved, but existing load models do not represent those things, okay? So if we just adopt the existing ones, okay? Also, DRA is a DER, distributed energy resource aggregated model, quite a generic model to represent the aggregated behavior of the DERs. It's a good model, but it should be up. Those parameters should be adequately parameterized, right? And if we adopted that model and also, then we can somehow implement ride-through capabilities. Okay. Also, as I said, we are improving that standard requirements. Also, we can somehow reflect those behaviors, improved behaviors in the model. Right? So, depending on the models we use, our study results are quite different. Right? So, it's a transmission line trip event, and because of the lowering voltage, and the DERs are responding to those events, so that it could be there. So models, simulation studies show the DERs could be tripped, and also it can increase the contingency size because of the unexpected trip PVs. So so if we somehow improve our practice, okay, LVLT capability, also improve the DRs, it also shows that we can somehow minimize the trip to PV, but it also indicates the importance of the modeling, okay? So it's kind of situational awareness in the planning stage. So because, I mean, I included this slide because to show the increasing contingency size as well as the importance of the modeling. Okay, we are improving this part these days in Korea. So also it depends on the loading conditions here. Sorry for the Koreans, but this is for the loading condition and off peak because of the increasing DRs. I mean PVs. Our system is very big actually, but our load even becomes less than 40 gigawatts. Okay. And then the system becomes quite weak, and also transmission line events could cause a voltage drop, and the DRs could be tripped, so that we can experience a very large contingency, okay, even larger than our existing standard of 2 nuclear power plants trip. Okay, that's just a brief introduction to the issues we are facing, increasing contingency size. See? Okay, so now let me talk about Jeju Power Grid, one of the topics. Okay, it's an island here. Okay, a very beautiful island, especially known for Honeymoon Island. Okay, so so when it comes to the power system of Jeju Power, it's a total capacity. Okay, and also a net load peak, springtime. But it becomes quite close to 1 gigawatt in the peak time, and also, but we have a lot of renewables coming in the Jeju. Okay, its penetration level is already over 20%. Very interesting system in that because this system is connected to the mainland. This is so-called Honam area, southernmost area. It's connected to the system through HCBDs, high voltage DC. And especially they are line commutated converters, means they are very dependent on the grid dynamics. And very interesting observation is that the Jeju Island, because of the renewables, it becomes quite weak. And this Honam area, 20% of the PVs of the Korea are installed in Honam area, and this area becomes quite weak. Yeah. So very interesting system. Okay, and this system actually I proposed this system to be an IEEE test system recently. So it will be quite a somehow you can find that there's a system available for your study as well. Okay, so based on this actual Jeju system, we made a test system for IEEE. So renewable penetration is 20%, and because of the increasing renewables, we will have an additional HVDC as well. So, so Jeju number 1, once again, so-called line commutated or current source to converter, CSC. So here, this you can see some numbers here. Okay, and we will have third HVDC, and it's gonna be operating in 2025. Okay, 200 megawatt is a symmetrical monopole, but it will be namely modular multi-level converter. Okay, so in San Francisco, the first commercialized MMC was installed, right? And the same technology will be utilized here, but you will have some control mechanisms to stabilize the Jeju Island system. Okay, it's coming from the ABB, now Hitachi Energy. Okay, so this is for the Jeju HVDC system. Now, when it comes to Jeju, power grid is relatively small, and because of the changing dynamics, we are improving. So EMT modeling and simulations are very important for crucial decision making. So so we have initiated this activity. So we conducted a very detailed EMT modeling of Jeju Power Grid, but Jeju has a lot of interesting components, okay? And also including HVDC, FACTS, and also inverter-based resources. Using existing techniques is going to be very challenging to model in the EMT environment by the PES CAD EMTDs. So as you can see from the ARCAT Texas efforts, also AMO, Australian Electric Market Operator, also some other HICO, Hawaii, and cases, we actually we try to reinforce our EMT modeling practice by using parallel network interface and high performance computing. Okay, we initiated that one so that we can somehow expedite the process. Okay, so by using multi-core. So using single core, it takes, a day, but we just expedite the process so that within 30 minutes or 20 minutes, depending on the operating conditions and study purposes, we can conduct EMT simulation studies for Jeju Power Grid. So that's a big improvement here. So one of the studies we did through EMT studies is that Jeju wants to be on the carbon-free island. The CFI stands for carbon-free island by 2030. It's a bit political declaration, but we were interested in really how in realizing the zero carbon power grid by 2030. Okay, and so here's it's a typical process, right? We develop scenarios, operating scenarios, and we consider the peak case. And we have to have must-run generators for frequency stability, also balancing the demand, okay? Considering some contingencies. So it used to be a minimal number. We operate more than 4 in practice. But somehow can we reduce this must-run generators by employing, say, grid forming technologies? If it is the frequency stability is the problem. So when it comes to this base case, so synchronous generators takes 17% of the load. Now renewables, although we have more renewables, but it has to be curtailed, okay? So 7% of the renewables has to be curtailed to maintain this 4 must-run synchronous generators. And we have HVDCs, 3 HVDCs. We envision number 3 is working, and it's quite flexible actually. VSC, one of the benefits of VSC, voltage source converter based HVDC, is that it's quite controllable, right? Depending on the operating conditions. But now it provides power from the mainland, okay, to the Jeju. So this is the base case. So when it comes to power electronics penetration level, it is about 83%. Now, we want to reduce the must-run generators, okay? And then replace this amount by renewables. Then we don't have to curtail the renewables. Right? It's a curtailment of renewables is a big issue in Jeju Island. Okay? So we want to minimize the curtailment by improving our operational strategies. So that we can improve the penetration level of the renewables without any curtailment. That's the base case, but you can see that the system should be weaker than the base case. Now, because now we have deployed the existing energy storage systems, namely GFL, grid following type. That's the existing one. And is deployed distributed in strategic locations. And total amount is assumed to be 130 MVA. Or in another scenario, we instead of GFL, we consider the GFM. So GFM is the technology is actually being evaluated in Jeju Island. Okay, we are one of the team actually in evaluating the actual performance of the GFM. And so we want to compare the benefits of a GFM with reference to GFL, okay, by conducting this very detailed simulation studies. So this is the scenario development. So here, 90% of penetration level of the power electronic components. Okay. Now also to evaluate how weak the system is, so we often do calculate SSCR or ESSCR, right? So in the point of interconnection, we calculated the SSCRs, okay, to see the weakness in a conventional way. And these are very important resources for frequency control, okay, and so they are set as desired as specified by the Korean Power Exchange. It's a KPX. And then we incorporate some scenarios, usually contingency, right? Okay, so I said a voltage-induced frequency band. So transmission line trip can cause voltage changes, and that could cause some issues in the frequency, and it may trip the generation as well. Okay, and we considered other scenarios, credible scenarios as well, but I didn't include these scenarios for the benefit of time. So transmission line fault, generation trip. Okay, then so in the base case, full generation case, right? Because of the single phase line trip in here, that's one of the benefit of EMT studies. We can include the single phase trip as well, and because DRs are quite sensitive to even single phase DR, the trip, and accidentally. And it happened in the US as well. According to the NERC disturbance report, that some generators could be tripped accidentally or correlated with that event. So we just considered these generators are tripped somehow. And we also consider the performance of the existing technology, GFL, ESS. They are normally do not provide power, but it just responded to the event. Unfortunately, existing GFL's technology. So actually, even GFL ESS is an additional asset to the system base case, but this combination cannot handle this operating condition. Okay? Because of the contingency, we lose 2 generators, but the remaining 2 generators with the support of the GFLs does not stabilize the system. That's what we observed in the simulation studies. However, if we deploy GFM instead of GFL with the same amount, very interesting observation is that GFM can help stabilize the frequency. Okay? So that stabilized the system. Okay. So by the way, I can deploy, I can distribute to the PPT slides for your review later. Okay. I already sent that slides to Cozy. And so even we considered this as the base case and consider additional. Okay, so now it becomes the base case, and now we add the same fault and we lose these generators. Then basically we lose all of the synchronous generators. Okay, and we want to double check that whether we can operate the system. So it can even operate the zero carbon power grid. So interesting observation is that it can stabilize. It can stabilize the system. Okay, the zero synchronous generations. So GFM only. I'm not saying that we have to. We can operate. We should operate this way, but this this operation even survive. So we can accomplish zero carbon power grid. And so because it's a very detailed simulation studies, we can see the LTC operations and also very detailed the IBR characteristics. So VSSC. We improved the VSSC control techniques by incorporating grid forming capability as well. Okay, so we have expanded the scenarios and explore the scenarios, various scenarios, and double check all of the interesting operation studies. But basically, the simulation study shows that zero carbon Jeju power grid is feasible. But of course, we have lots of homework still. So, but anyway, it's a good, interesting observation. So this part for the Jeju power grid EMT studies, and we have established some certain framework for conducting EMT studies. Now, it will be coming into our planning and operational practice, okay, in a few years. And also, we have observed the benefits of grid forming. Now, after gaining some confidence in EMT studies, we have expanded this study to more larger system. So we consider the Honan area. Sorry for the Koreanness as well, but it basically is a alert. Okay, kind of NERC alert. Okay, so it's alert from KPX that contingency size increases. It's a big impact. It's going to be a big impact. So it can lead to a blackout in the whole system. Okay, so it's a 5.2 gigawatt of contingency could happen. And also it indicates our LBLT should be improved. And as I said earlier, we have now 20 gigawatts of renewable, and most of them are PVs, and 20%, 40% are installed in the Honam area near Jeju. Okay, that's just the basic information about Korean power system. Now, we have conducted the existing PSSC, okay, so-called RMS or phasor domain simulation studies. But once again, that practice does not capture the issues of the DERs, right, properly. So we have conducted EMP studies of this Honam area. So all of the components reliably modeled in the PSS ER reflected in the EMT studies. Also, we added the EMT dynamics, okay, on the very important components. It's an even bigger system than Jeju, okay. So it takes more time, actually. Also, of course, more efforts to build the base case. But we have somehow automated some process so that we can double check the steady state power flows are okay, so that we can start the EMT studies from the very basic knowledge of the PSSC studies. And so as again, we want to explore the issue of uncertainty and contingency impact, okay, size basically, and also the area, affected area, and also interesting system, a very interesting system because two systems are very weak and connected to through HVDCs. Okay? So we want to see the impact of the contingency in mainland on the Jeju. Okay, because usually we will see flows from mainland to Jeju. Okay, this is the general power flows. So we want to see the impact of Honam event. Okay, so impact of Honam PV disturbances is a fundamentally voltage-induced frequency event. So a three-phase transmission line trip cause under voltage issues. Some voltage, some voltage problem causes some voltage problems, and very voltage sensitive IBRs are tripped, and we lose IBRs and we lose frequency stability, and because of the frequency problems, we lose IBRs, and so that because of the under frequency relay generators and those are tripped, so that even it can cause some a very big problem in Korea. One disclaimer is that the whole Korean power system is not modeled in the EMT studies yet. Some parts of the remaining Korean systems are equivalently represented in EMT studies, so it doesn't say you cannot rely on this information, this simulation results. Okay, but it just implies that it could cause blackout in the system because somehow equivalent system can represent the remaining characteristics in a limited way. Okay, so also here when it happens, it can cause Jeju Island. Okay, so here voltage mainland. So here, so this is the fault. IBR chart and unstable voltage. So voltage of the Jeju. Okay, and so we are showing graphs along the time and the fault event. So somehow stamp to the time, okay, and see the impact. So a very interesting observation, also lessons. Okay, we should more carefully plan the system, also operate the system. Okay, so because of the trip and somehow PVs are not equipped with the ride-through capability, then we may lose a whole PV, say, then we lose this amount of PV, then also it shows that IBRs are tripped. Also, IBRs are distributed, right? So we change the set value somehow so that we can see the gradual impact. Also, they do not behave simultaneously. Okay, so somehow event propagation, also their changing behaviors can be shown in the simulation studies. We want to more, we want to elaborate, to incorporate those behaviors as well, okay, by refining the models. So very interesting observations, okay. And if we lose only 10% of the PV somehow because of the improved LVLT, then okay, we can see some changes in the Jeju HVDC controls. I will not talk about in detail about HVDC controls, but we explore the way to coordinate HVDCs to handle some operational issues as well. But anyway, it shows that LCC, okay, line commuted converters, they are very depending. Their operations depend on the grid conditions, so they can suffer from commutation failures, right? So it clearly indicates those behaviors and also restoration behavior. So a bit detailed, a bit different perspective. Okay. So we are in that process. Okay. So also I mentioned earlier that Honam area is we are using equivalent model, but we want to minimize the uncertainty of the simulation results by equalizing the system, right? So co-simulation is also becoming a practice as well. Okay. We have developed T-set RTDS co-simulation platform earlier with the Capco and also PowerTech Lab. So up until now, I talked about some challenges, universal challenges of stochastic distributed IBR dominated power systems. Okay, growing complexity in operations and planning, also some uncertainty, right? And many of the PVs are installed in the distribution systems, so the TND interactions are becoming more important. And so I put some good words so you can easily find it. But anyway, it's a big issue in Korea. So we want how we can coordinate all of those resources, controllable resources, as a big homework and a big research topic. And always modeling, analysis, controls are big part of power systems engineering. And also, there's a company named Korea Grid Forming. It comes from our lab. So it's a recent startup company, and we provide interesting grid services to the power system. So by providing grid forming, we can somehow minimize the curtailment. Okay. So an interesting business model in Korea. Also, Jeju Power Grid as a test system, IEEE test system has come. Okay, so it's gonna be available soon. Okay, so last PES general meeting, we introduced this idea and received the good comments. Okay, so we will somehow deploy this system in the near future. Okay, so this much for my presentation. Thanks for your attention. So I will be happy to have your comments or questions.
Thank you for the wonderful presentation, Dr. Fu.
Thank you.
Do you have any questions? You can also, type your questions in the chat box if you want. But before starting, so this test system will be available soon, right? And do you include all kinds of generated dynamic models inside? Like frequency control, voltage control, everything inside?
Oh, yeah. We actually, we showed that model, including all those dynamics earlier. But
Okay.
it's up to you, okay? Because I mean, from this very basic configuration, you can explore lots of interesting operating scenarios, right? So
Yes.
yeah,
And then
hopefully we can
also,
also, okay,
yeah, and
yeah.
also like a synchronous generators will be like a gas-fired power station and also coal-fired power stations, you said. And so which one is coal-fired? Which one is gas-fired?
Oh, it's a benchmark system. It doesn't include that. It's just that idea that
Okay, so which means, for example, the primary frequency controller uh, is the same for both type of power plants.
yeah. So number one HVDC is the primary frequency controller, and the remaining have actually synchronous generator have the governors, but they are set governor free, so do not operate that governors in certain conditions. So number one is the actually this is the number one. It controls the frequency, and yeah, as you said, yeah, we have governors in the generators. Okay.
Okay, so the governor module is also included in the test system.
Right. Okay. Actually,
Inc
that test system is based on PSCAT EMT, unlike those with PSAC or PSCAT, PSLF models.
And have you ever validated the model response? I mean, comparing the simulated response and then the actual event recorded
Oh,
responses.
yeah. So one of the interesting projects CAPCO does, and is to deploy PMUs, phasor measurement units. So we will have some measurement data so that we can compare the actual response. But we are still in the validation stage, right? Like many other countries.
I see.
Yeah. So we are just making the platform so that we can now improve our practice significantly.
Okay. So by the way, can you open the chat box? I mean, chat
Oh, yeah.
window. Yeah, I think we have some comments or questions in the chat window.
Oh,
So
yeah. Mhm.
yeah, you can see two comments.
So we, yeah, that is, this is about fault analysis and legacy relaying. Okay. I talked about deploy. So basically, we are observing some issues. Many other people notes on the impact of inverters on the protection. Okay, but somehow Korea system, I mean, Capco doesn't want to change their practice protections systems, right? Integrity of the protection. So, very interesting thing I want to share with you is that even though you deploy GFM technology, don't affect our protection. So limit your short circuit fault current contribution to the system to I mean, like any other grid following inverters. That's an interesting requirement the CACO imposes. So they see that they need to improve their practice, change their practice, but up until now, because of the, but I mean, somehow they restrict us to affect their system, protection system. Okay, but they have to change their practice. I mean, because of the increasing. Oh,
Thank you.
so on the first page, I have my email contact information. So, oh, so just we have relays. So they just Capco just to disconnect PBs. So we have SNS, and so I mean your PPs will be disconnected soon. Okay, kind of information is sent to the PP owners, and then they just disconnect. and they put some priority. So I mentioned some interesting business model, right? Through the GFM stay. Capcom first disconnects PBs without any write-through capability or any grid support mechanisms. And so by having this type of grid supporting ESS, or is also a supercapacitor based ESS, it can help stabilize the voltage of the bus where PV is connected. So, but even though with that, I mean, those PVs could be without any existing write-through capability. It's a legacy one, so that it lacks in low voltage write-through capability. Then, if they buy this type of technology, then they are not curtailed. Okay, listen.
Okay. You mentioned like a voltage-induced frequency event multiple
Yes,
times in your slide.
right.
And so, do you usually consider the mixture of voltage and frequency events for the contingency analysis in South Korea?
No, no, no. That has not been investigated yet. Okay, that's not a practice here. We
I
just
see.
consider a single generation trip or transmission line trip, but we observe this is coming. Okay, also KPX, although it didn't lead to the blackout of the system, but they were just surprised to see that it can happen in Korea.
I see.
Enlarged contingency. Okay.
And
So
also, yeah, this time you primarily focus on the like a PV trips, but I think you must have wind farms as well. So,
yeah.
what about consider? I mean, do you consider like a low voltage right-through requirement for wind generations as well?
Oh yeah, yeah. We'll have very strict requirements, but wind is still very minimal. Okay, but we have a
Oh,
very big and also ambitious plan to build the offshore wind here. It's a southern sea, south. Okay, sorry, the West Sea. Okay, here China, Korea, and Japan, and so here we will have a very large offshore wind, and we will have a multi-terminal HVDC in the planning. Okay, then we have to consider the operational complexity of the wind. So yeah,
okay.
but yeah, we will have some winds, but still PVs are dominant.
I see.
Mm.
So yeah, you try to analyze, I mean, consider the operation of the protection devices of the PVs in your simulation studies. And then I saw the low voltage protection operation in the simulation scenario, I mean, simulation results.
Yes.
And so, for example, in the US, if
Hmm.
we follow the latest IEEE standard,
Yes.
28P 2800, and then
Hmm.
they usually I think consider the dynamic reactive support
Yeah, that's
during the
right.
fault.
Hmm.
So in this case, probably we can avoid the like a
Hmm.
low voltage issues
Right, right.
following the faults. So what
Yeah.
is the status in South Korea now?
So it's quite that kind of capability is quite minimal here because we just adopted. We just allow them to be connected to the system. But now we impose very strong requirements and also reactive power current injection capability, right? To support the grid is coming. But uh, so it should be coordinated with other devices because it can cause some. So anyway, it will be coming. So one of the observations I shared with you is that we can minimize the contingency size by having uh, that low voltage write-through capability, right? So here it becomes without any capability, the contingency size is 6 gigawatt, but it can minimize that impact as well by having that capability. So it
I see.
provides that lesson as well. Okay, the importance of having that capability, also importance of having that good model. So,
But can we get to know the PVs with LVRT requirement and then without AVRT requirements? Can I
Oh,
get to know the
that's
percentage of these PVs in South Korea?
so CAPCO provides a certain information, but in the simulation studies, it's hard to provide. I mean, reflect that information because CAPCO also quite limited information, right? So we just distribute randomly in some sense. Okay,
I
with
see.
a very minimal information. Somehow we can maybe this percentage of PBs that have this capability, then it may provide some beneficial effect, say. Okay. But we hopefully we will have more detailed information, more accurate information, so we can improve our model fidelity, so we can get
Excellent.
some more reliable simulation results.
I think we have one more the question or comments in chat window.
Is the plan to look at bigger and bigger systems, or is it for compact? Oh, so one of the projects we are conducting with the CAPCO is to have a EMT planning practice. Okay, so here system-wide EMT modeling analysis is gonna be the practice of the CAPCO in a few years, say, because we are developing a tool. So if we can somehow expedite the EMT simulation process, say in 1 hour, 2 hours, that we can somehow conduct the supplementary EMT studies. Okay? We can add that studies to their practice. Okay? Yeah, we are not believing that EMT studies can replace their existing planning practice, but it would be very beneficial. So we can focus on, say, Honam area, the most problematic area, or Seoul, and also we'll have a HVDC to the load center, Seoul area, Seoul metropolitan area, and the study should be very detailed, actually, okay? And also HVDC. And unfortunately, this is gonna be line committed to the HVDC, very, very vulnerable to grid conditions here. We will also have a PBs. So the operating conditions becoming very complex. Uncertainty is growing, so EMT studies should help. Of course, it's not a single bullet, a silver bullet, so we have to improve other practices as well. So I talked about PMUs and also micro PMUs and the waveform measurement units they consider, but it's a lack of powers. I mean, human resources definitely just many people are just studying AIs and computer science, Korea medical school, but we have to engage more passionate young engineers in this area as well.
Yeah, thank you. I
Yeah.
think the time is almost like running out.
Oh.
So, yeah, Professor Fu, an excellent professor from Yonsei University. It is great to have you in the IEEE PES Footier section webinar today. And then, folks, our next webinar will cover relevant topics, which means grid forming converter simulation studies in Germany. And then the speaker is an industry engineer from Germany. And this will be held on February the 14th, starting at 11 a.m. in California time. And then the next webinar after next will cover the demonstration project with 100% renewable energy sources. The speaker is a utility engineer from Japan. And this will be held on April the 1st at 3 p.m. So please stay tuned and then enjoy the rest of the day. And again, Professor Fu, thank you so much for the wonderful presentation.
Thank you so much for having me. Thank you.
Yeah.
Sure.
Bye for now.
Bye.
Thanks, Koji.
Yeah, thank you, Max.